Deep.
What's up?
How you doing?
Good. It's been a while.
It has. Some of us have to take vacations once in a while.
Yeah, some of us.
Yeah.
Some of us, on the other hand.
You're too young to take vacations.
Oh, come on.
I like the shirt.
I'm always on vacation.
That's a good sign. So we must have a very important guest today.
Yes, we absolutely do, because I'm wearing the shirt. Yeah, I'm not wearing some other random color or anything of the sort. We're here to discuss your favorite topic, Charles.
It is?
Yeah, this is your favorite topic.
Simulated.
Yes, there you go.
On.
So we're here today with Young.
Cool. Hi.
And he's been on the team for a while. Why don't you give us a little bit of an introduction?
Yeah, so I joined the team back in 2010 in August.
Nice.
So it's 8 years.
Anniversary.
Right.
Yeah.
Yeah.
Probably today. It was definitely today.
Not today. Not today. So when I joined the team, the team is pretty small. At that time, it's called Windows Fabric. I believe someone else said that.
Yeah.
But my name is pretty common. But I had to choose something, to differentiate myself. I chose Win Fabric. I can still see it.
Yeah,
I didn't change it.
Yeah, it's still there. Well, you shouldn't change it.
Okay.
Yeah. There's no reason. Now we know.
For the first a couple of years, I worked on the lease driver thing, our failure detection stuff. Work on the federation and lease, and after that, I kind of work on in parallel lease and PLB. PLB is placement and load balancing. And later we changed it to CRM. We tried to change it to CRM, Cluster Resource Manager, because when we talk to the customer about load balancer, they always confuse with network load balancer.
Correct.
So we try to avoid the confusion. So we try to change to CRM.
Yeah.
Which is not very successful because within the team, people still call it PLB.
Yeah. Yeah, but this is important to know because if you look at the traces that are generated by the PLB, so if you look at the actual service fabric events that show up in people's diagnostics logs, they're all tagged with CRM. So externally, it is and should be known as a cluster resource manager because really it's balancing resources. It's not balancing traffic or load per se. But we still refer to it as a PLB. And for the course of the video, will you be referring to it as the PLB?
I'm more comfortable with that.
Okay, sure. All right.
All the public document, we always mention CRM.
Okay.
And also for the trees, you just mentioned exposed to the public, we call it CRM.
Right.
That's something. Right. But a lot of traces for the internal diagnostics or investigation, we still use the PLB. So we kind of use the two terms in parallel.
But can we just for 1 second though? I mean, it's called the placement load balancer for a reason.
Yeah.
Right. So it does have similar behaviors, doesn't it? Like, why would you call it that if it doesn't actually behave in a way that's similar?
Similar but different.
Of course.
Yeah. So that's why we treated placement. There are kind of like a few different actions in the PLB component, right? For new replica placement or new service. I probably should give an end-to-end scenario.
Yes.
When user or either through the service manager or through the API to create a service, first we got the request of service, and FM will ask PLB to create a few replicas for the service if it's a singleton partition. And at that time, we use a placement logic. We want to do the placement as soon as we can, but in a balanced way.
Okay.
But for balancing, it's just like we schedule the balancing with the interval. But for each balancing run, we want to take longer to have a better result. That's why we call placement balance.
Understood.
Sweet.
Very algorithmic.
Yeah. Well, we're going to go into all of that.
Beautiful.
Yeah. So to start out with, could you tell us a little bit about sort of how the PLB fits in with the overall picture in Service Fabric? So we've gone through a lot of components in these videos. We've met a bunch of people. We've covered things like RA, hosting, FM, FMM. And for those of you that are watching and may not know what those are, please check out the playlist inside Service Fabric. It's got a bunch of informative videos that cover those topics. So given that people have that background knowledge, I think it'd be great for us to get a sense from an architectural perspective where PLB sits into the picture and how it communicates with those different components and the various contracts it has.
Sure. So to speaking in a simplified way, PLB work very closely with FM, Federal Manager. So you got a global view from the Federal Manager by, FM PLB stay in the same service. So you can just like a function call into the PLB to pass all the necessary information. And based on the global view, PLB run its algorithm and generate the results and pass back to FM. That's kind of like commands. FM, after receiving the commands, most of the time I would say, if you pass to RA, the RA is the guy really done the job, right? To execute the commands. This is probably to.
Feel free, yeah. So we talked to AP a little bit about RA.
I guess, yeah, I
Yeah.
believe that's the case, right? So it's kind of like, this is a PLB, and this is a FM. So they work very closely together. And FM passes out the commands and moves to the RA to really,
Execute.
right.
Right.
FM, PLB stay on the same node, right?
Same process as
Same
well?
process, yeah. And RA is on each node, right?
So what does the PLB do in like one sentence, if you were to define the purpose of the PLB?
To basically do optimization. We want to do a balancing of the each load on each node, right?
And when you say load, you actually mean the services or the partitions that are deployed on that node.
Right. Yeah. We have aggregate view of the aggregate load on each node, right? We try to move replica around to shuffle them so the whole cluster can be in a balanced way.
So it's fair to say that it's optimized on making sure all of your nodes are doing the same amount of work at all times.
Right.
To have some kind of harmony in the cluster.
Yeah.
A balanced load of computation.
Yes, very good. That's why it's called a load balance. And now we're back.
We're back. So enough with the CRM. That's customer resource management. Isn't that what? Yeah.
It's the same
Just
thing.
kidding.
Customer relationship.
Customer relationship
Yeah,
management.
yeah.
No, but right on, man. I mean, this is interesting. So,
CRM, I just want to mention, probably is also not a good name because people confuse with another famous.
CRM.
Yeah.
It's true. But anyway, so let's dig into sort of how it works. So, what does it actually do to optimize the placement?
Yeah, I guess, yeah. There are a few things I want to mention here is, from the beginning, I guess, it had a few different actions, right? Placement, just like what we discussed. There is another action called constraint correction. And third one is a balancing. Right?
So what's the difference between placement and balancing?
I guess we just discussed that. I can put it into a little details. Placement is when we only do it for the new replica, right? Because we want to, the service want to, the new service creation want to do it as soon as we can. So the placement usually done very soon, like 1 second, 2 seconds, or half second, depends on the configuration. But balancing can be run like up to 2 minutes. So this is by scheduler once in a while, right? But placement is like kind of like run very frequent. Depends on if you have new service or not. Right? The constraint correction also is very important because we want to avoid the violation or try to minimize the duration if we want to see some violations once in a while. Right? Some people may say, why do you have the constraint violation in the first place? Right? Most of the time it's because of some failures. In a perfect world, we probably won't see any violations because all the placement and balancing, when we do that, we are according to the constraints, right? But if some failure happens, then probably there will be some violation. We need to correct them as soon as we can.
And these constraints are what we call like placement constraints and stuff as well?
Yeah, that's my next thing I want to mention, right? This is probably first. Second is we have a bunch of constraints we try to follow.
Okay.
First one is a placement constraint. This is pretty easy to understand in my opinion, right? So it kind of like each node has a certain property. You can think of the node, use a color, right? It's a red node, or yellow, or blue, you know. For your service description, you can specify this service can only be on the blue node or red node, right? So for the new replica placement, we will follow that. Also during the balancing, we only shuffle the replica. If you specify the replica only be on the red node, we only move to another red node. So why is this important and useful? Because in the cluster, different nodes may have different properties. One example is like, some machine may have like SSD, some may not have, right? For your service, want to access to the fast disk, you want to have the put on the node has a SSD, right? This is place constraint. We also have like FDUDs. So this is a fault domain. Some people call it failure domains. Same, upgrade domains, right? One basic rule we want to follow is for the fault domain. So you have like 3 domains, right? The fault domain is a tree structure we try to follow, right? This is a FD1, FD2, FD3. For a partition, we try to spread the replicas evenly across the domains. Like you have 3 fault domains, they're going to be 1 replica each. If you have 4 replica partition, and it's going to be like 2 replica here, 1 replica here, 1 replica here. So for some reason, if you have 2 replica in this domain and 0 replica in domain 3, then that's a violation. We're gonna move one replica from either the domain 1 or domain 2 to domain 3.
Makes sense.
Yeah. Okay, let's see. Yeah. I want to give example. If some failure happens, right? Say, if some node in this domain 2 go down for some reason, and there is 2 replica just disappeared. We still have 2 replica in domain 1 and 0 replica in domain 2. Then we're gonna move replica to domain 2 to make the even.
Makes sense.
In the general case, but there's one catch here. In the node down case, we wait like a while. By default, it's 2 minutes. We don't want to do this very right after node down, because the node may come up again. Then we're gonna have another replica here. We're gonna move them again. We try to avoid that.
Okay.
Yeah.
So you're waiting to make sure that the node is actually down.
Yeah.
And what happens if the entire fault domain goes down? So suppose you have to place 4 replicas. Is it always going to be 2 and 2, or is there ever a case where it might be 3 and 1?
No.
2 and 2.
So if the domain totally go down, we're gonna create another replica in domain 3. Yeah.
Cool.
They're gonna be 2, 2. Yep. So we have another constraint called affinity.
This is one a lot of people don't actually know about, but it's super useful.
Yeah. So during the service creation, you can specify, say, for example, this is service 2. So you can say, I want to be affinitized with service 1, right? That's a part of the service description. Then during the placement, we're gonna place a replica together with service 1 replica. And also by doing the balancing, we also move them together. So to make sure they always locate on the same nodes. Yeah, we also have like a node capacity. So this is specified on the node description. for each metric, you can specify a value. And when we do the placement and balancing, we make sure the total load on the node is less than the node capacity.
Is this also where resource governance comes into play?
Yes.
Perfect.
Yeah. And we also have another thing called scale on count. So this is used together with applications. This is to make sure, say the application, for example, there is one application has a number of services. Each service has a number of replicas. Want to make sure the replicas only stay on like no more than 4 or 5 nodes, depending on the what's the number specified for the scale outcome, together with the application description. Yeah, this is basically there is another one. Preferred location.
That's interesting.
Yeah. So you can internally this is used for like a few different things. One thing is the standby location. You may have a persistent stateful service, and the replica is down on some node, right? When you place a new replica, you want to place on the same node, right? You may have states where a lot of data already on the node. If you place on another node, you do a lot of copy. Sometimes try to avoid that. Yeah, that's basically all the constraints we tried. There's some constraint I didn't list here, but we also follow like replica exclusion.
Okay.
There are no 2 replica on the same node, but there are some requests that we, provide option that they can't be on the same node. But
Yeah.
it's not happening yet.
Okay.
Yeah.
But all of this stuff is best effort, right? It's not actually guaranteed.
It's guaranteed. Like
It is?
Yeah.
Cool.
Plus constraint by default, I say. Affinity, no capacity, those things are guaranteed. FDUD, I actually don't remember. We changed it a few times, but this is by priority. If you specify the constraint priority to be 0, then that's guaranteed. If it's greater than 0, it's 1 or 2. This is based on the
Ranking.
Right. Then we try to
So people can actually change that? People can...
Yeah, you can change that.
So where do you go to change that? Where do you
this
change
in
that?
the PLB config. It's a global configuration. It's cluster-wise. Yeah.
Wow, I didn't even know that. So that means that while setting up my cluster, I can actually say, I want certain elements I want the PLB to actually prioritize things differently than what Service Fabric decided to prioritize things based on.
Yeah.
That's interesting.
Yeah, I did not know that. So that can change the entire way in how efficient or
Sure.
how suited to your needs it is. So if you care only about affinity and you don't care at all about some of the other stuff, then I didn't know that.
It's great. There's so many knobs.
So many knobs.
Impressive.
Yeah.
But I mean, at the end of the day, it's the data integrity that drives everything.
Correct.
Right?
Yeah.
Consistency.
Consistency.
At all times.
Forgive me. Integrity, consistency.
You're forgiven.
Right on.
So for the PLB itself, we have like a list of views. Like I believe when Mansoor talk about framework manager, we already talk about that. Like you have a node table, you have like services, and you have like partitions, right?
So this is the global sort of view that Mansoor was mentioning.
Right.
So does the PLB have that or does the FM have that?
FM has a detailed table. We also have each table for node services, but it's a simpler version. We don't care about the stuff relevant to PLB itself, right? For load balancing purpose. FM has to deal with a lot of other details. We have like replicas. So we have an aggregate view on each node of the total load, right? So suppose they have like some replica from service 1, some replica from service 2, so on, right? But we maintain an aggregate view of the total load, and what we try to minimize is standard deviation across the nodes. That's a simple. That's our goal.
Okay.
Yeah. So each replica can have different loads, and the loads can change. How user change that, right? So we have a report load API call from the individual nodes. They call into FM and update the load for each replica. By default, it's 5 minutes interval.
So why did we pick standard deviation? Why not just range? Like min load versus max load on a node?
Yeah, that's a good point. We can do that, but we find out standard deviation is easy to calculate, easy to reason.
I guess as someone who doesn't have background, I would think range would be much easier to calculate than standard deviations. That's interesting.
Now, standard deviation has very standard calculation formula, and it's well formalized. And
Method, yeah.
So if you can have a really small standard deviation, that means the load is pretty balanced. Yeah. But I agree with you. User range is also fine, but we just didn't use that. I would say either way is okay. Yeah. So this is the background.
Yeah.
Right? So how do we do this? How to minimize the standard deviation? There are a few different ways. You can do it's called top-down or greedy or some other things. The algorithm we use is called simulated annealing.
His favorite word.
So it's basically a controlled cooling process. If you're in the metal cooling business.
Exactly. So it's from metallurgy.
Right.
Right on. You guys have adapted it too, but you're still dealing with temperatures, quote unquote, in some sense, right?
Yeah. So temperature here is just like obviously it's not really temperature. It's just parameters you control how slow the processor can go on. This is basically just to simulate or mimic the process of using the metal cooling process. It's the same thing. Right? So what do we do is first generate a random move. The move here is just like a replica 1 from node 1, or I would say C current node to the next node, right? It can be node 1 to node 2. And how do we evaluate if we want to do the move or not, right? This is just like a random move. It's just like a temporary move. We're not, it's not in the final move yet. So we calculate the standard deviation. If the standard deviation is smaller, it's less than the previous one, that means that the move is good, then we're gonna use it. So we define the probability, it's called P. If the diff here, calculate the difference of the energy or standard deviation is the same. If the diff is less than 0, the P equal to 1. If the difference is greater than 0, we use a formula. So it's gonna be like, so it's minus the difference divided by T. Here T is the temperature. So we want to achieve is when the temperature is high, something like this. So this is 1, right, the probability. This is temperature. So when the temperature is high, you want to have a higher probability choose a bad move. And also, if the move itself generates a bad move, when I say bad, it's the difference is large enough, want to have a less probability to do that. So when the temperature is high, it kind of like what should I say this? It kind of like climb a hill. Some also call it hill climbing, right? So, or in this case, it's go down the hill, right? You try to avoid the what's it called local optimal problem, right? Because if you always want to choose the next node with the less energy was smaller standard deviation, you may easily get into a local optimal. So in some case, you have to use certain probability to choose a bad move, so you can get over the hill and to really find out the the global optimal. Yeah.
So explain that. What would be a local optimum in the case of a cluster?
Okay. So maybe one example is this guy here. So the overall standard deviation is less than before, but it's not the optimal way. The best maybe you shuffle this guy somewhere here and this guy here and another one to here.
Fair enough.
Then you get
A better
Right.
standard deviation.
distribution. Yeah. It's hard to see from here, but if you
Yeah. I think
You got the
viewers
point.
would get the point.
Yeah.
of that, yeah.
Mm.
So then, with that context in mind, how do we get over the hill? So what do we do using that exact scenario?
So because if you always want to do a better move, you want to just from the next move compared to the previous move, you try to only use the zero. Then for I guess from the energy point of view or standard deviation point of view, right? It's kind of like this. There are high one here. It's easier to explain, guys. Explain. Suppose at beginning you're here, right? So there is a better one here. You always go down here. That's why you go down here, right? But actually there is another one here, which is global, the minimal standard deviation. But after you reach the local optimal point, you cannot choose the guy here, right? But with the simulated annealing, it's possible because at the beginning the temperature is high. The probability to choose a bad move is also pretty high. But you may choose some point here, and you may get over this bump. And
But doesn't that mean, so in this case, suppose this didn't exist. So suppose we stopped right here, then going over the hill is bad, because this is actually global.
No, in the next iteration you may come back, right?
Okay,
Yeah.
so is the idea that the temperature would be low enough at some point that we wouldn't be able to cross, because we
Right.
just don't think that there's a good option on the other side of the hill?
So from this formula you can see if the temperature is really low, and the probability of this one is zero. Then
Yeah.
yeah.
Exponential. Sure.
Yeah, that's why to maintain a slow temperature dropping process is important. That's why sometimes we run like 2 minutes. It's just the drop really slow to make sure that when you got a local optimal and you cannot find the global optimal, then you stop back to the local optimal.
Interesting.
Yeah.
And so now that you brought this up, what is the relationship between optimizing the cluster from a perspective of the least amount of standard deviation across load versus the time it actually takes to get there? So is there an argument to be made that there might be moves because they're faster to do, we should just do them to have some kind of balance, or is it that we treat the situation to have infinite resources from a time perspective to achieve like as much optimization as possible?
Exactly. That's why we have I didn't mention that here. For the balancing, we have 2 steps. We have it called faster balancing, and we have a slow balancing. Or they want to change the name slow because they think it's bad.
Right, because we don't want slow balancing.
The major,
All balancing should be fast. Fast and faster.
The major difference between the fast and slow is how fast you drop your temperature. Right?
Interesting.
Yeah.
So the likelihood of climbing the hill is lower.
Yeah. So the slow balancing we run after 3 or 4 by default. Okay. 3 or 4 fast balancing. We still find the cluster is not in a balanced way. We try the slow balancing to see if we can do a better job. But if after a few fast balance run the cluster is already balanced, we won't run the slow balancing. So fast balancing 10 seconds by default.
So when you say 10 seconds, does that mean it goes through this phase every 10 seconds? Or does it mean
we run up to 10 seconds.
So the whole process will take?
Yeah, so if it converge before the 10 seconds run, now we just stop there. when I say converge, that means I cannot find a better move anymore.
Okay. And how often do we do, so we talked about how this happens in the case, I could call it a trigger, right? Which is like there's a trigger, there's a new deployment.
Right, you can
this
think
is,
of that.
This is kind of triggered by something being in a warning state or something not being healthy.
Yeah, this is 1 second, like, within a second we're gonna run that.
Okay, and then, but how often do we do this?
How often?
Is it always running in the cluster at all times? FM
No,
is, okay.
no, this is configurable by default. I think like it's currently 5 seconds or 30 seconds. I don't remember exactly. We want to change it to 30, but I'm not sure if we change it or not. So you can think of like every 5 seconds we thread command to check if we need to do random balancing or not. We need to run, then we run it. But this is configurable. Some people configure like 1 hour or something, and which bring up another topic is like how do you control how frequent you want to run the balancing? Right? There are 2 parameters or configuration you can use.
More knobs.
Yeah, it's called like the first one is called balancing threshold. The second one is activity threshold. So by default, this is equal to 1. This is a 0. 1 means it's always on. So because for the balancing threshold is calculated by the max divided by min. Max is like you have like 10 nodes in the cluster, and so you have 10 nodes, right? No 10. Some nodes have like for example, low is 100. Some node has a low like 50. So when you calculate the ratio is 2, right?
So it is max load over min load. So that we are looking at range in some way.
So the 2 is greater than 1 by default, right? That means the class is not balanced. But if say, okay, I don't care too much about balancing. I do care if they're really imbalanced, right? Then you can specify this to be 3, right? Then we come up with like 150. Oh, it's pretty balanced. We don't need to do run balancing, right? Yeah.
Can we do fractions? Could I set it?
Yeah.
Okay, cool.
Those are just examples.
Yeah.
It's a double.
Yeah.
Yeah. So activity threshold is like when in a cluster, say it's not busy at all. Like say each node has like a capacity is 100, and the current node is like 2 or 3 or small values. You say I don't care about balancing in that case, even if they are greater than balancing threshold. I don't want to run balancing.
So what's the trade-off? So we've got 2 different options here. So this one sort of informs service fabric that there's a range of imbalance that you're okay with.
Right.
And this one says for stuff that's not big enough or not important enough, I'm not particularly concerned. I can it's under the radar. I don't have to worry about minuscule workloads. But what about the trade-off against actual processing happening on the machine? So obviously balancing is not free. Right. It must take up some resources. It obviously spins up a process, like you said, and eats up some amount of compute. How expensive is it, and what's the trade-off versus just running my workloads reliably and consistently and having the fastest I/O versus correctly
I would
balancing?
say like the running of load balancing itself consumes some resources, but that's not very important because it's only run on that node. It's only run on one node.
Where the primary of the FM is.
Right. A lot of times the user feel that the number of moves is a big cost to them. Right? Yeah. So say the load balancer generate like hundreds moves or even thousands moves. They have to do like really execute those moves. That can cause chaos in the cluster. That's people try to avoid most of the times. They don't really care about the resource consumed by the PLC.
I see. Yeah, because we get that quite a bit, which is a lot of partition reconfiguration. And
I get all the time.
Yeah.
Like, obviously hundreds of instances where
partition reconfiguration is too high.
Yeah.
So would you say that in that case, so suppose I'm a user today, I have a cluster, I'm seeing partitions move around like crazy. and I open up an incident, and I'm like, hey, way too much partition configuration. It might be affecting my my uptime effectively for some endpoint because you're moving my replica around so much. What would be your advice? Do I play with these thresholds, or what do I do?
First, if you didn't set this, first set this, right? If you can tolerate some, imbalance, set a higher balancing threshold, and set higher activity threshold. If that's not enough, you may think of setting some a balancing interval to be longer. Then we don't run balancing that often, even we reach the threshold, right?
And what is the downside of disabling the PLB?
Then you're gonna have a very imbalanced cluster, and if some nodes running hot, you may get stuck. Things may not working. You may
Sure.
lose availability, right?
But would that also mean that I don't get to use these things?
No.
Okay.
If you just disable balancing, we still run this.
Correct, because placement is still happening.
Placement still happening. Constraint correction is still happening.
Sure.
So
But balancing is not.
right.
Can you ever disable all of it?
You can also disable constraint
Correction.
correction, but you cannot disable placement. If you disable placement, the whole thing is not working.
Nothing's gonna get deployed.
Yeah.
Okay, cool. That's interesting. This is
But
whack,
these
right?
aren't things you'd want to do.
Well, I don't think so. Yeah. From a best practices perspective, it makes perfect sense to have balancing turned on. And I mean, very simply, it's at some point you're running at scale. You want to make sure your machines are running equally hot or equally cold, because you don't want to have a machine become a liability. You don't want one of your nodes take on too much workload. So even as you're talking through like moving these variables around, like I don't imagine going up beyond 2 is something that you even want to do. I feel like maybe if I wanted to go up beyond 1, it could be like 1.2, 1.3. I don't imagine that the balancing threshold would be an actual whole number jump, because it could be very costly. Because even to have one machine running half as hot and one at 100% is already a liability. One thing I do want to dig into a little bit more is node capacity. So lately we've had a lot of situations effectively where resource governance, if administered correctly, would have helped a lot.
Right.
And we're seeing this inside service travel clusters. We're also seeing this in the world in general. Especially with people moving and using Linux service today, where Linux has a tendency to kill processes that are taking up too much space on the operating system effectively without prioritization of what it kills. How should somebody leverage resource governance correctly to make sure that one, service fabric is using as much as it can on the node, but two, it's also optimizing the way in which things are placed.
So by default, the resource governance should be on, right? We govern the resource currently by two metrics. First is CPU cores, right? And the second is memory. It's called memory in MB, so megabytes, right? So these two things, if you didn't specify anything, we're gonna detect them automatically on the node, and we're gonna set a limit of them. So it should be on.
Interesting.
Yeah.
How do we do that?
You don't need to do anything. We do it by you.
Okay, cool.
Or you can say, okay, there's a configuration. I cannot remember the name. It's just auto detect or something. If you set that to be off, I believe by default it should be on. Right? If you set to be off, you need to set a limit for this yourself, right?
So we detect.
You say,
on the
okay,
machine.
yeah, you can say, okay, I don't trust your auto detection. I know my computer has how many cores or how many memories. I will set a limit myself, right? We're gonna limit the resource by your specifications.
Well, so it might not just be used in a setting where you don't trust auto detection. It could be a way in which you could then say, I have a node that has 100 units of computation, and I only want service traffic on 80.
Exactly.
And I want to use 20% for something else that I just can't afford to not have run. And that's interesting because you can limit then what service traffic thinks it has access to, right? Because it's a logical limit.
Good point.
Yeah. So it's not just because you don't trust us. Because if anything, you should trust us. It's this consistency is the one thing we stand for.
Okay.
Yeah. Okay. And then, I mean, one question I've wanted to ask is we've obviously. So this is cool. I would have never thought of applying metallurgy and like concepts like temperature and finding ways to alias them into distributed systems to have machines that, pardon my pun, run equally hot. I mean, but what if you were to do this again? How would you do this? How would you rebuild the load balancer? Would you do things differently? What are some things that have worked well in the design that we have, and what are some things that we're still working on?
I think the overall architecture is pretty good, and the algorithm is also very good. There are things we need to improve, definitely, right? Like say, currently we rely on the load reporting from the replica. In the future, we may have something like a load projections, right? Based on the past pattern, we may predict or project what's a load value in the future, and we may do something before that, so to have a what's that called? The current algorithm is and the maximum is more like on demand, right? We react to the load change in the cluster, but in the future we may
You want to predict.
right, yeah.
Proactively optimizing
Yeah.
rather than reactively optimizing.
And using machine learning and stuff. Too.
Right, and also today the metric we have a pretty simplified view of the metric property, right? In future, some possible improvements is to have different properties of metric. Think about it, like a metric, they can have quite different. How should I say? It's nature, right? Suppose you have I know some customers use a number of connections or session. Like how many users connect to the servers, like it's 20 or 50. This can be very dynamic, and it can go down quickly from some number large than to 0. But some other values like a disk space or something is quite different from the connections. Today we allow user to use like a logic value for the metric, right? You can define your own metric, but the metric can be quite different. Today we have a simple value of them. This can be improved.
So you can use more complex variables too.
Yeah, we can treat them differently. Right?
And what about optimizing the simulated annealing algorithm? Do you think it's perfectly optimized?
We have been, try to working on the tuning and stuff. We have improved that quite a lot.
I'm sure.
Yeah.
And folks can see it.
Yeah.
There'll be a link to it in this video. We've already shown it before.
Yeah.
Look at the code. There's actually not a lot of code.
No.
It's surprisingly simple. I mean, quote unquote. Really great work. This is fun because this is also highly algorithmic. So people who want to geek out on the code should be geeking out on this. And there's the face right there, folks.
Well, I mean, he also pointed at certain things you could do to help improve the algorithm itself, right? So for those of you that do want to go and contribute a PR to the Surfstar code base, this could be a very cool space to attempt to do that in.
Amen.
Solving a very complex problem in a not so complex way.
Absolutely.
Or understandable way, I suppose.
For sure.
I need to
gotta do your famous.
The famous. I have to ask you a question that you did not expect coming into this room. What is your favorite kind of bicycle?
The regular one.
Is it on there?
I think so, right?
Yeah.
Yeah, here.
It's a bunch of regular.
So do you bike? You cycle?
It's only for fun.
Only for fun?
Yeah.
Okay.
Okay.
Cool. Thanks so much for your time. Take it easy.
Right on, man.
And we'll catch you soon for another one.
Absolutely.
Yeah. Take care.